No, yes, you're right. Hard machining in the traditional, there was one company that was doing hard machining, DCS. These people were doing hard machining because they had a very rigid, stiff milling system, and those people were using hot isostatically pressed zirconium. It was from a Swiss company called Metoxid, and these people were doing the sintering of these big blocks, and then hot isostatically pressing it before that you could buy it. And one of the features associated with that is that not only did it have higher strength material, but it also was more translucent. Why? Because you had less porosity and you had less scattering of light at those interfaces between with that porosity. So it had some aesthetic attractive components as well. No. Usually the harder, it's a much harder system. And the problem with the DCS system, why it's virtually gone out of business, is that it was taking 5 or 6 hours to mill a 2-unit bridge or a 3-unit bridge. And secondly, the cost of that machine, because it was much more rigid, quality of the cutting tools and things was such that it was 3 or 4 times the price of the soft milling systems that were available. Absolutely. It's extremely hard material. As I said, these people were taking 5 or 6 hours to mill a 2-unit bridge. And what you found that most people that bought one of these milling machines was that they were not milling zirconia, they were milling titanium. Because it was just not financially viable to mill zirconia. That's correct. No, unless you have the stress-induced transformation, you do not get toughening. Yes, you are correct that with cerium oxide you get less destabilization of that system. The problem with the yttrious systems is that you don't get as high a strength or toughness of that as the cerium system does not give as high a strength as the yttrious systems, unless you have a nano-composite type of structure which has got alumina and other components in it. But now you have much greater opacity to that system. But yes, why is it not giving rise to water transformation or water-induced transformation? Because cerium oxide is a 4-valent ion, and it is going to replace zirconium, which is a 4-valent atom. So it's not so many oxygen vacancies that are left into that structure. So it becomes less tolerant or more tolerant to the water-induced transformation process. It still shows a little bit of this problem, but nowhere near as bad as before. Yes, it is, because the sintering conditions are much more difficult, because you also have to put increase of alumina or something of that into that system to be able to well, what the real problem is that with the case of the ceria, the grains grow much more rapidly than they do in the yttrious system. And the consequence of that is that the normal sintering conditions, the grain growth is bigger. You have 3 to 5 micron grain size versus sub-micron grain size in the system. The problem with those coarser grain sizes is it decreases the strength. Now, if you want to get the strength up, you have to introduce alumina particles or nanoparticles. And these are what we call as grain boundary pinning functions. So they pin the grain boundaries so that grains don't grow in the sintering. So now you get finer grain size. And so in this way you get smaller grain size and you get higher strength in that structure. But you could also make it more difficult for the complete sintering process to occur. And so this, what you're talking about, is you've got more porosity in that system. Secondly, it's much more opaque, because now you've got two materials with different refractive index in the one structure, the aluminium oxide and the yttrium oxide. So now it appears much more opaque compared with the case of just straight zirconia. Because with zirconia, it's one refractive index, and so basically you've got more light being able to transmit through that system, provided the density is high enough. Have I confused you at another level? In many ways, I would prefer minimal surface treatments after firing. In many ways, it does. Normally you're having a milling process, and you're milling the green structure, the soft structure. So this will lead to a very rough surface. And to me, this is sufficient, because that roughness associated with that. Whereas if you do any other process, such as grinding or grit blasting, you transform some of that tetragonal structure to monoclinic. Now there is this question, does that create a nucleation for further growth processes after you put the porcelain onto that system? And does this influence the adhesion and bonding to the system? We've just done a whole series of studies in terms of looking at different processes, and what we find is that putting it directly onto the zirconia S5 is excellent. We do not see cracks running along the interface. The cracks are always propagating in the porcelain, adjacent to the interface, not at the interface structure. I have heard of other people who have grit blasted the zirconia and put porcelain, and they have reported that the crack is running at the interface rather than in the porcelain adjacent to that. So to me, that implies that the bonding and adhesion to, if you like, treated surfaces where this transformation has occurred is much less than the case where you've just left the structure as it is. Certainly, as I say, I don't see the need to do it, because usually with mill structures you have sufficient roughness in its own right to provide that locking attachment to that structure. Some people are arguing that you should put a thin bonder layer before you build up the main porcelain. The role of the bonder layer is in a way to seal the surface. So if you have sealed the surface, then because it's so thin, you don't get this moisture-induced transformation in that system. And after that you can put a thick layer of porcelain and build it up. Now the water in that doesn't get access into the zirconia, so it doesn't cause that transformation. But if you put the wet layer directly on the zirconia, you can certainly see the transformation at that interface. Are there other questions? Right, well again, thank you very, very much for your attention, and I enjoyed the questions, and hopefully you've learned something about these systems. Thank you very much.
Thanks for Professor Swain for this nice and valuable lecture, and we hope to meet again.